Yes, well, this is a long presentation as well, so I'm going to encourage you to maybe look at some of the documentation behind this. These and other reports are available through the Wood Buffalo Environmental Association. This afternoon, Kevin Percy, the executive director, will be giving a little more detail on this topic here. Our objectives here were, again, as George pointed out, to get at more real-world and site-specific types of information in terms of emission. And this study focused on wind-blown dust. It complements previous studies which were discussed earlier on the big truck exhaust and also on the upgrader facilities. And this is a very important topic because it's one of those area sources that has the largest uncertainty. So here's our objectives. And what I'm going to focus on is the second one today, which is to really look at the dust suspension potential from different types of surfaces that are in the oil sands regions. And the other topics are dealt with in more detail in the reports. Well, certainly windblown dust is one of the most visible types of emissions that we see. And it can be on a small scale, or as in this case from Alan Legg's picture, on a very large scale, depending upon the wind speed and the exposure to the surface. Now, most of the time, in the wintertime, there's snow cover. And so one would think that windblown dust is not an issue. And yet when we put de-icing material on the road, in that time during the thaw, it becomes a big issue as well because there's a large reservoir of material that are there. Now, if you look at the national inventory, what you see is that it's a very large portion of the particulate matter emissions. Now, these are surely overestimates. We've looked at these in a variety of inventories over the years, and we just don't see this much. And the reason for this is it tends to be more of a localized phenomenon, so that some of the material that gets in the air falls out of the air before it transports over a very long distance. And that's a good thing in many ways, because if we have an isolated operation, it's not going to transport a lot of that material to places where people can breathe it. However, in the oil sands regions, we have many different types of emission sources. Not all of them are associated with the mining operations either. Many of them are associated just with the transportation of people back and forth. The de-icing material is a good example of this. We have two types of reservoirs. And typically, most soils in their natural state are fairly stable. They are what we call limited reservoirs, and this is because either most of the suspendable material has been removed, a crust is developed, or there's a vegetative cover over the surface. It's the unlimited reservoirs that are of greatest concern when we're looking at dust suspension potential, and these generally result from activity that takes place and disturbs the surface. Now, a lot of work has been done on this over the last 50 years, and this is an example of how this used to be done. This is the University of Guelph's wind tunnel. One of my colleagues, Jack Gillies, graduated from there, and this has gone all over Canada. It's gone to the Dust Bowl in the U.S., it's gone to Owens Lake, it's gone to Africa, and it's gone to Antarctica. Now, you can see that this is not a very practical way to do it. So the people that developed this, Bill Nickling and some of my colleagues, put some efforts in developing a more portable system, and this is the system that they've developed. It's a very small chamber that you can see has a flat blade that simulates the shear stress near the surface. And the faster that blade rotates, the more that shear stress is, which simulates what happens when we extrapolate from a wind tower, which is usually about 10 meters, down to the surface. And that follows a logarithmic relationship in most cases. So by estimating what the shear stress at the surface is, we can relate that back to a wind measurement that we might take. And you can see that there's a pretty good relationship between the two wind tunnels. Now, none of this is, there are large error bars on all these things, and you can kind of see this is a logarithmic scale, and you can see the reproducibility of both methods is quite large. Nevertheless, when we look at it in a relative sense and with relationship to different wind speeds, this gives us a good idea of what surfaces are likely to be emitters and which ones are not. Tested 64 surfaces, all up and down in different areas, and these represent both ones that are associated with the mineral extraction, the storage piles, the tailings ponds, as well as other surfaces that are natural and surfaces that are created for other activities. There's a lot of unpaved roads in the region. Even paved roads have a certain amount of dust on them. The way the system works here is to have both continuous measurements of particle suspension as a function of particle size and different filters that take the chemical measurements. I'm not going to dwell a lot on the chemical measurements here, But part of the rationale for the chemical measurements is to look at fingerprints, chemical fingerprints that one can identify at different monitoring sites. And I'll show some examples of those at the end just briefly. And you can see the setup in the upper right-hand corner here. It's fairly compact. The real advantage is that rather than have to disassemble the very large wind tunnel, we have a very small unit that we can move to adjacent spots in the same area so that we're sampling essentially the same surface type of material to get both a variability and also enough sample for chemical analysis. There are several types of winds that are likely to cause suspension. The first example is not really very common because this is kind of a ever-increasing wind speed, and this is done just to kind of look at the maximum amount of material and the maximum velocities that would suspend the material. So that's the first test in the upper left-hand corner. The second test is intended to look at what wind speeds really cause the most suspension, and this is what we call the threshold velocity that we achieve. And you can kind of see in the example there, you need a fairly high wind speed to start getting a certain amount of suspension. You notice there's two particle sizes there. There's the PM10, which is the part that kind of gets through our mouth and gets caught in our upper respiratory tract, and the PM2.5 that gets down deep into our lungs. So both of these are important for their health related. Then finally, we look at a step mode where we look at what the total emissions might be under different maximum wind conditions. And you can see some examples there in the lower right-hand corner of how one depletes the surface in one place. So you want to have a surface that's fairly uniform so you can move the unit around to get enough samples with these various types of tests. Well, one of the interesting things here is that any dust reservoir that appears to be limited under normal types of wind conditions can become unlimited when we have very high wind conditions. This isn't the case for all surfaces, but in some cases, the forces become so high under large winds that they blow off the surface crust and they get down to underneath the surface. This is especially the case when we have like a stabilized storage pile where we have a crust on the surface, but the crust mitigates against suspension until the wind's so high that it blows the crust off, and then you essentially have an unlimited reservoir. We can kind of look at the various types of winds and their suspensions, and it really is hard to classify these by just like unpaved road because it really depends upon the activity that's taking place on that road. You can see in the top panel, we look at various wind speeds and how much might be suspended for the lowest 10 cases. And then the bottom panel is the highest 10 cases. Now, the scales are quite different because the lowest 10 surfaces are much lower than the highest 10 surfaces that you can see. You can also see that for the lowest emitters, you need a fairly high wind speed to get any suspension whatsoever, whereas you start seeing suspension for the highest emitters at much lower speeds. And of course, you have some unpaved roads in the top panel, which are the less, and these are typically more kind of access type roads that don't have a lot of activity on them. So typically what happens on these roads is you're not seeing a lot of the mechanical motion that grinds up the surface. And then of course when you're looking at a haul road like you might find within a mine, you've got big huge trucks that are continually turning over the surface, and these create unlimited reservoirs and a lot of potential for suspension. And you can kind of see the differences in there too. What tends to happen with a fairly limited reservoir is you get kind of a gravelly appearance on the surface. You can see some of the gravel on the top diagram there. And this actually helps to prevent the suspension because even though those are very small rocks in the surface, they tend to attenuate the shear velocity near the surface so the smaller material doesn't suspend. You can see with the more unlimited reservoir that you have a very fine material on the surface. There's not much of a granular nature to it, and so it is able to be suspended more rapidly. What you can kind of see also is that some of the stabilization conditions, like watering, really are effective. They're quite effective. The disadvantage of watering is that sometimes if you do it on a road where people drive, it's just like having a wet situation after a snowstorm where the pickup or the car gets covered with the material, it tracks it out on the paved road, and then it just kind of leapfrogs its way down the paved road. So one of the techniques that is used is the corrugated shakers that kind of get stuff off the trucks. And then wheel washing is always a very effective mechanism to get rid of that. Here's an example of the watering, and you can see a comparison of a road surface. This was the same road using a part that had been watered recently and was moist compared to one that wasn't watered, and you can see that it's quite effective in terms of reducing the emissions at the various wind speeds. The other important thing that really makes a big difference is the disturbance. So in some cases, like on storage piles, there are stabilization chemicals that are put on top of these. And you can see kind of the two spots here in the bottom area. You can see the stabilized part on the right and the unstabilized part on the, stabilized on the left and the unstabilized on the right. And you can see that the stabilizing material that's put on there, which generally kind of clots the small particles together, is quite effective. The real question that comes up is how long does it last? And a lot of this depends on the activity that's taking place on the surface. Generally, these materials tend to last for quite a while unless there's activity that's breaking the crust that they form on the different surfaces there. Now, the chemical composition is quite different depending on the different types of areas that are sampled. Some of them have a lot of similarities in them because there's kind of the same basic soil, it's just that there's different additives to them. So what we see here is when we look at the tailing sand, we see quite a bit more of the organic material than we see in some of the others, which is typical of what happens because originally the tailings had bitumen in them, and there's still some residual amount that's left over. When we look at the haul road, we actually see more of the surface dust that's involved in it. The coke pile on the lower right, as you might expect, has a lot of carbonaceous material and a lot of the black carbon, a lot of the material that's more graphitic in nature. And then, of course, if we look at a limestone quarry, not to big surprise, what we see is there's a lot of calcium carbonate and a lot of calcium oxide because that's why they're quarrying there. They're quarrying to feed the cement production units that are needed. One of the big differences between the types of dust that you find within a mine and that you compare with ones that are outside the mine is in the bitumen-related quantities that are in there. And that's probably not a big surprise here. Here we see the N-alkanes, which is an organic substance that's part of the bitumen. It tends to coat the small particles. It tends to be a coating on them. So what you find is you actually get increases. So the PM2.5 fraction generally has more of this coating on the particles than the PM10 because you have a bigger surface to volume ratio. And you can kind of see as you move forward, comparing it to bare soil from a forest, kind of natural soil, that this is kind of a fingerprint. This is a fingerprint for this type of material. So when we combine this with the other mineralogical fingerprints that we saw before, the aluminum, the silicon, the calcium, and other things, this gives us the potential to separate this type of material from other contributions when we take an ambient sample. Well, our conclusions, I've just kind of touched the surface of the major study, and as I tell you, if you've got interest in it, there's much more detail in the reports. But there's a large variability in the suspension potential across a region that the chemical composition demonstrate that we can see distinct fingerprints for certain of the sources that we should be able to distinguish at receptors. And that the amelioration measures, where they are applied, are really quite effective. And they're making a big difference in terms of what that dust suspension potential might be. Now, how can you use this data? The way we usually do this is we take some emission factors that were made for particle size that are much larger back in the 1970s at a couple of coal mines, and we apply those everywhere all the time. We need to get more specific, and we have the technology to do this. We saw some good maps in the previous presentation of how we can grid things up. We can superimpose those on things like land use, on roadways, and then we can associate these data, these size distributions, these reservoir sizes, these threshold velocities with those. Then we can couple these with some of our empirical and theoretical meteorological models, the same things we do to transmit the emissions from the source to the receptor, to estimate where and when we might get those emissions. Now, certainly there's still a lot of uncertainties, but this at least gets us away from this 85% of the inventory as kind of the concept that we're using in terms of the fugitive dust, because it gets it more specific to the highest emission potentials and the transport distances based on the particle sizes, which would settle things out. Then finally, the chemical profiles can be used as input to what we call receptor models, which infer what the contributions might be from the chemical compositions that are commonly measured at the sources and at the receptors. And finally, we need to acknowledge the people that helped do this study and sponsored it here, and you'll hear more about that later in the meeting. So that concludes the presentation.
Perfect. Thank you. So are there any questions? I see a couple people getting up, so if you just want to get over to the microphone, if you don't mind, that'd be great. And we could have a question for either of them. I think we have a few minutes.
So are you saying that you could sort of create sort of risk maps, kind of like pest disturbance maps? So these would be sort of like emission or?
Yeah, that's probably a good concept. I would call it an emissions potential map. I mean, I would say you'd look at it in two ways. One would be kind of based upon a distribution of wind speeds that you would have over the regions. Where might we have the greatest difficulty? This would maybe help to focus some of the stabilization measures in place. And then when we're actually doing the modeling for specific episodes, we would like to have as accurate emissions as possible to see how much things might get there. But yeah, that's a good point. We can probably even do a zone of influence around a source with that type of an approach.
And how did you incorporate disturbance? I know I saw it on one of your slides, but you just had sort of frequent disturbance. But how did you quantify that and incorporate that into?
Well, we went to specific sites that we knew were disturbed, so that this would have to be one of the classifications that you put in the GIS. What are the areas that are likely to have a disturbance? You know, typically a mine haul road would be one classification where you've got stuff going back and forth. And this is where it's kind of a moving target as well, because these things are moving around all the time. So maybe with some of the newer technology, you know, we've got these drones you can fly over to kind of see where activities are. This might be something that gets incorporated in the process.
Great. Some more questions? A couple more yet?
Have you been, has there been any effort to compare your results in terms of fingerprinting to the, for example, the snow depositional kind of studies on what appears to be substantial winter dust?
I'm not really aware of that yet, but I think that's a good thing to start looking at. This is one reason we looked at the size distributions as well as both the PM2.5 and the PM10 composition. So I think the data is amenable to that. That's not kind of within the scope of our project.
John, a recent paper by Trent University looking at base cation deposition indicated, or would seem to indicate, that this dust is actually having a beneficial effect in the developed, sort of the intensive development area in terms of neutralizing acid deposition. Any comments on that?
A lot of dusts do contain a neutralizing factor, you know, because you see in each one you saw a bit of the carbonate fraction, which we measured explicitly in there. So one could use certainly some of these results to look at what the capacity might be if it were to deposit in certain amounts. I suspect that the most neutralizing part would be like the calcium carbonate, which would react with the acid very rapidly.